Good day, grade 11s. Hope you're doing well. Today we're looking at limiting reagents, and in principle I would just like to rewrite this equation again. Okay, do you remember I explained to you with the video regarding stoichiometric calculations? I explained to you that normally with this you will get information about one of the reactants, and then you will have to calculate either information about the other reactant or about one of these products. And do you remember I told you it's about like getting onto a train, like you will be given information about mass or volume, and you use your molar mass or molar volume to change this information into moles. Then you use your molar ratio, and then you use your molar mass or molar volume again to get whatever is asked. Okay, so this is the normal way of thinking regarding stoichiometric calculations. But with limiting a reagent, you will have the following scenario. It will look like this. You will have information about both of these, and then they ask you, which one is the limiting reagent, or they might ask you determine how much of this substance is formed. So first of all, both of these will not, it won't be perfect, you understand? So it won't be like, let's say you need, if you've got 20 grams of A, then you need, let's say, 30 grams of B, but now they only gave you 25 grams, or let's say they only gave you 15 grams of B. Do you understand then that the 20 grams of A needs to react with 30 grams of B, as an example, right? But if you only have 15 grams, that means only 15 grams will react. So it would be depleted, but you will still have some of A left. In this case, you will still have 10 grams of A left, because only half of what you need was present, right? So in this case, B is the limiting reagent. Can you see? And B will determine how much of C and D is formed, not A. And that's why this is so important, because it doesn't matter. You can have a ton of A, but if you only have 15 grams of B, a bunch of A will be left. So the 15 grams, like I say, in this example, B is the limiting reagent. So that's the concept. That's what it's all about. So now let's do some calculations, because that's truly where you test if you do understand this work. So the first example, I'm going to take the example from the book again. And this is the example on page 193 in your textbook, Study and Master Grade 11. And it reads as follows. In the thermite reaction, 20 grams of aluminium are mixed with 65 grams of iron oxide and ignited. Determine which substance is the limiting reagent. Okay, so we have our balanced reaction, and that's always the first one that you need to write. So we know it's aluminium reacting with iron oxide, and this is a very exothermic reaction once you get it started, and it forms aluminium oxide and iron, which is a liquid because of the temperature, but that's not that important in this case. And remember, what's the first step? You always balance. Okay, so based on the previous video, you remember we've got 2 aluminium on that side, so we need 2 aluminium here. We've got 2 iron there, we need 2 over there, and the oxygens are already balanced. So this is a balanced equation. Okay, so now we need to ask ourselves the following. What do we have? We have 20 grams of aluminium, and we have 65 grams of iron oxide. So we need to determine if, and you can take 2 paths now. You can say, okay, I have 20 grams of aluminium. How many grams do I need of iron oxide to react with 20 grams? And you do that calculation, and if that amount that you get is less than 65 grams, then aluminium is your limiting reagent. But if that amount that you calculate is more than 65, then iron oxide is your limiting reagent. So that's the methodology, that's the approach that we are going to use while doing this. Okay, so first thing, so I'm going to approach it in that way. I'm going to work with aluminium. I'm going to start with that one. I could have picked any one of them. It really doesn't matter. Both can lead you to the same conclusion. So I'm going to start with aluminium. Okay, so now I say, okay, molar mass for aluminium is 27 grams per mole. Therefore, the amount of moles is mass divided by molar mass is 20 divided by 27. And we will get a value of 0.74 mole. Okay, and based on our equation, we know that 0.74 2 moles needs 1 mole. So 0.74 moles needs half of that. Okay, so then you can say, therefore, 0.74 divided by 2 moles of iron oxide is needed. Okay, now we just do the calculation. 0.37 mole. Now we need to calculate what is the mass of 0.37 mole of iron oxide. So the molar mass of iron oxide is then the next thing that we need. So it's, okay, iron oxide, so it's 2 times iron, which is 55.8, plus 3 times 16, which is oxygen, right? It's 3 and the 2. And if you do the calculation, it's 159.6 grams per mole. So now we can calculate the mass needed. Okay, so therefore mass equals moles times molar mass. So it's 159.6 times 0.37. And that is equal to 59.11 grams. Okay, let's recap to see what we have calculated. So we started with aluminium. We said, okay, we have 20 grams aluminium. That's what we're starting with. We're not looking at the iron oxide, we're just starting with this. Then we used molar mass to determine the amount of moles that we have. And that's what happened here. Okay, now we have the amount of moles. Now we use the molar ratio to get to iron oxide. You understand? So that means if 0.74 moles of aluminium, you need 0.37 moles of iron oxide. And that is equal to 59.11 grams of iron oxide. So this is what we know. We use the molar mass to calculate that. So 20 grams reacts with 59.14 grams of iron oxide. So which one is in excess? The iron oxide. Because after the 20 grams is completed with the reaction, there will still be 5.89 grams of iron oxide remaining. So can you see that aluminium is our limiting reagent and iron oxide will be in excess. Okay, so this is the approach. This is the way of thinking. So we need to still write our answer here at the bottom. Therefore, aluminium is the limiting reagent. Okay, so that's how this works. I would like to use this now just to introduce 2 other concepts here as well. This is also in the textbook, page 194, with the example, and we're talking about percentage yield. Okay, and it's easily understandable. You'll see now as I do the calculations. But I want you to not use the method in the textbook. I don't think that is at all a valuable method. It can be very confusing, but for some of you it might work, so if you want to, go for it. But I do it a little bit differently, and I want you to notice how I do it. Okay, percentage yield. Okay, this is a theoretical concept, right? 2 moles will react with 1 mole to give 1 mole and 2 moles. This is theoretically, it would be perfect like that. Theoretically, that 20 grams will need the 59.11 grams that we've calculated. Okay, so now theoretically, if 20 grams of aluminium reacted, we know that 0.74 moles reacted, right? And according to the molar ratio here, 2 moles aluminium would give you 2 moles of iron. So we know that 0.74 mole iron will form, right? That's what we know. And we know the molar mass of iron is 55.8. Therefore, the amount of grams formed would be 0.74 times 55.8, and that would give us 41.29 grams iron formed. And this is theoretical. This is if there's 100% yield, this is what you will get, right? It was 41.292, but I'm just rounding off to 2 decimal places. So this is in a perfect environment, 100% yield. This is what was formed. Now, in this example, they told us that 20 grams of aluminium reacted, and let me just get to that example, but only 35 grams of iron formed. Okay, so 35 grams was formed. Where if it was perfect, to 100% yield, we would have had 41.29 grams, right? So now they ask, what is the percentage yield? Now it's literally just the following calculation. Percentage yield is equal to 35 divided by 41.929, sorry, my mistake, 29 times 100. And that is the basic principle of this. So then you will see you get an answer of 84.77%. So that was the percentage yield. Okay, so it's based on the theoretical concept versus the practically what did you get. Okay, when you always work from the limiting reagent, and our limiting reagent over here was aluminium. Okay, we did not look at the 65 because that was not the determining factor, it was the aluminium. One last concept for this video, and that is the percentage purity. So this is applicable, let's say for instance with mining, you've got like ore, but only a certain amount of that ore is gold or is iron. So you've got iron ore, and you've got a total sample, let's say with a mass of 100 kilograms, but of that 100 kilograms, only 70 kilograms is the pure iron, for instance. So that's the percentage purity. So you just look at the mass of the pure product. Note, mass. Mass, it's based on mass. Divided by the mass of the total sample times 100, and that's the percentage purity. Okay, that's it for this video.